we motivated the need for Laplace transforms as a way to solve differential equations that involve discontinuous functions. And we looked at some functions with discontinuities when we studied step functions. Step functions are good for modeling a process that suddenly turns on, like an electrical switch, that goes from 0 to something all in one moment. However, in some scenarios, a large force can be applied in a short time, like an electrical surge or the force of a hammer. To model something like this, we want to define a function g of t that occurs over a short interval centered around some time we'll call t equals 0. That is, for values of t between negative tau and tau for some small positive number tau. This function depends on what we pick for tau, so we'll write it as g of t equals d sub tau of t. And we'll define it as 1 over 2 tau for t between negative tau and 0 otherwise. Now the total impulse of the force of g of t we'll call I of tau, and it can be found as the integral from negative tau to tau of g of t. Notice that with this definition, I of tau is 1 for every value of tau, because the impulse I is defined as the integral from negative tau to tau of g of t dt, where g of t is 1 over 2 tau on this interval, which is a constant that can be factored out, and the integral from negative tau to tau of simply 1 dt is the length of that interval, which is 2 tau. So we have 1 over 2 tau times 2 tau, which is 1. Momentarily, we will let tau vary, so it will be useful information to know that as tau changes, the impulse I of tau will constantly be 1. Now, in a theoretical impulse function, we want to consider this force occurring at a single moment in time. That is, we want to think about our time interval from negative tau to tau as tau goes to 0. As tau goes to 0, the function g of t, which we can also think of as d sub tau of t, has a larger and larger spike over a shorter period of time, since the impulse, the total area under the function, I of tau, is fixed at 1 for any value tau. If tau is large, and thus the time interval over which the force occurs is large, then the height of that force function g of t is short. But as tau gets smaller, and that total impulse, which we can visualize as the area under g of t, stays constant, the height of g of t gets larger. And as tau gets closer and closer to 0, we get more and more of a spike occurring at t equals 0. And in the limit, this spike will get infinitely high. We use this idea to define the unit impulse function that we call delta of t, to behave like the limit as tau goes to 0 of d sub tau of t above. In particular, we define delta of t to be a function with the properties that delta of t is 0 for t not equal to 0, and that the integral from negative infinity to infinity of delta of t dt equals 1, just like the integral of d sub tau of t equals 1 given by I of tau. We can generalize the above impulse function to have its spike at t equals t naught by evaluating delta at t minus t naught, effectively shifting the spike from t equals 0 to t equals t naught. This generalized version is called the Dirac delta function, and it has the property that delta of t minus t naught equals 0 for t away from t naught, and the integral from negative infinity to infinity of delta of t minus t naught dt is 1. To visualize this graphically, we have our spike happening at t equals t naught rather than t equals 0.